So next up, let's take a look at a couple of examples of these style problems. So for example, the sine of the inverse tangent of 3/7. So first thing we'll do is identify that we have the appropriate kind of composition and say the inverse tangent of a ratio is going to be an angle. Let's call it theta. So theta is equal to the arctangent of 3/7, which is equivalent to saying that the tangent of theta is equal to 3/7. That's the definition of an inverse function. So what I'm going to do is draw this angle in the appropriate quadrant and label two sides. Now, the inverse tangent is restricted to quadrant 1 and 4. If the ratio is positive, we automatically go for quadrant 1. If the ratio were negative, we would go for quadrant 4. So this will be our angle theta with our appropriate reference triangle. Tangent is equal to opposite over adjacent. So I'm going to label my opposite side as 3 and my adjacent side as 7. You now know two sides of a right triangle. Use the Pythagorean Theorem to find the third. So we have 7 squared plus 3 squared is equal to r squared, or r squared is equal to 58. That lets us know that r is going to be equal to plus or minus the square root of 58. Because it's a hypotenuse, it'll be the positive square root. Once you have your triangle labeled, you can go back to the original problem and say, what were we actually trying to find here? Once you've made that substitution on what theta is equal to, you're now looking for the sine of theta. Taking a look at the reference triangle that you've created, the sine of theta would be the opposite side over the hypotenuse. The opposite side over the hypotenuse would be 3 over the square root of 58. Easy peasy, lemon squeezy. Let's try this process again. Let's take a look at the secant of the inverse sine of negative 5/13. So first off, for an inverse trigonometric function, we will label it as an angle. So now we're saying that theta is equal to the inverse sine of negative 5/13, which is equivalent to saying that the sine of theta is equal to negative 5/13. Now for the sine of theta, the angle restriction that we used for this was from quadrant 4 up to quadrant 1. Positive ratios go in quadrant 1, negative ratios go in quadrant 4. Now sine is equal to opposite over hypotenuse. So I can label my opposite side as 5, my hypotenuse is 13. The hypotenuse should never be negative, but we do need a negative ratio. That means that the 5 should be negative. You now have two sides of a right triangle. Pythagorean theorem is the way. So once again, we'll label that as a squared plus b squared is equal to r squared. We're trying to find the adjacent side. So we square the negative 5, square the 13. That'll be 13 squared minus 5 squared. Please feel free to use a calculator for that. And a will be equal to either plus or minus 12, depending on the quadrant. Because we're in quadrant 4, and this is the horizontal side, that side should be positive. Once you've finished labeling your triangle, you can head back to the original problem, which would be the secant of theta. Secant is the ratio of hypotenuse over adjacent. Hypotenuse is 13, adjacent is 12. So the ratio that we're looking for is 13 over 12. Let's take a look at a couple more examples. Next up, we'll try the cosine of the inverse cotangent of negative 4 over 3. As we did for the previous problems, we identified that the inverse cotangent is going to be an angle. So theta is equal to the inverse cotangent of negative 4 over 3, which is equivalent to saying that the cotangent of theta is equal to negative 4 over 3. Now, cotangent, the angle restriction that we used on this was quadrants 1 and 2. 1 for a positive ratio, 2 for a negative ratio. This is a negative ratio, so it'll be in quadrant 2. Cotangent is adjacent over opposite, so I'm going to label my adjacent side as 4, my opposite side is 3. Because we're in quadrant 2, that means that the x-coordinate will be negative, so the adjacent side is really negative 4. You now know two sides of a right triangle. We'll use the Pythagorean Theorem to find the third. A squared plus b squared is equal to r squared. So negative 4 squared plus 3 squared is equal to r squared, letting us know that r squared is equal to 25. That would mean that r is plus or minus the square root of 25. Because it's a hypotenuse, it cannot be negative, so we'll label the hypotenuse as positive 5. Heading back to the original problem now. The original problem now states we are looking for the cosine of theta, which would be the adjacent over the hypotenuse. The adjacent side is negative 4, the hypotenuse is positive 5, so the ratio that we're looking for is negative 4/5. And we'll do one more for good measure. The cosecant of the inverse secant of 29 over 21. We have an inverse trigonometric function that is an angle. You know what? I'm sick of your face, theta. We're calling you alpha. Yeah, what? So we're saying that alpha is equal to the inverse secant of 29 over 21, which is equivalent to saying that the secant of alpha is equal to 29 over 21. The secant would be the hypotenuse over the adjacent. The restriction that we used for the secant is quadrants 1 and 2. So quadrant 1 for positive ratios, quadrant 2 for negative ratios. We have a positive ratio, so this will be in quadrant 1. 29 is the hypotenuse. 21 is the adjacent side. You now have two sides of a right triangle. Use the Pythagorean Theorem to find the third. A squared plus b squared is equal to r squared. So that'd be 21 squared plus b squared is equal to 29 squared. B squared is 29 squared minus 21 squared, which you can use a calculator to help you out. That would be 400. Therefore, b is equal to plus or minus the square root of 400, which would be 20. Because we're in the first quadrant, we want the positive one of those. Heading back to the original problem, we were now looking for the cosecant of alpha. If you'll kindly recall, cosecant's a hoe. Hypotenuse over the opposite side. Hypotenuse is 29. The opposite side is 20. That takes care of that.